3.6 Finding normal proportions. Areas under a normal curve represent proportions of observations from that normal distribution. There is no formula for areas under a normal curve. Calculations use either software that calculates area or a table of areas. Most tables and software calculate one kind of area, cumulative proportions. The idea of cumulative is everything that came before. Here is the exact statement. Cumulative proportions. The cumulative proportion for a value x in a distribution is the proportion of observations in the distribution that are less than or equal to x. So when you look at a normal curve, basically everything below x, like to the left of x, would be the cumulative proportion. The key to calculating normal proportions is to match the area you want with areas that represent cumulative proportions. If you make a sketch of the area you want, you will almost never go wrong. Find areas for cumulative proportions either from software or, with an extra step, from a table. The following example shows the method in a picture. Example 3.5. Who qualifies for college sports? The National Collegiate Athletic Association, NCAA, uses a sliding scale for eligibility for Division I athletes. Those students with a lower high school GPA must score higher on the combined mathematics and critical reading parts of the SAT or the composite ACT to compete in their first college year. Beginning in August 2016, first-year eligibility requires a minimum 2.3 GPA in high school core courses. Those students with a 2.3 high school core GPA who take the SAT are required to score at least 980 on the combined mathematics and evidence-based reading and writing parts of the SAT to be eligible. The combined scores of the almost 2.2 million high school seniors taking the SAT in 2018 were approximately normal, with mean 1,059 and standard deviation 210. What proportion of high school seniors meet this SAT requirement of a combined score of 980 or better? Here is the calculation in a picture. The proportion of scores above 980 is the area under the normal curve to the right of 980. We know that 980 is to the left of the center of the graph because 980 is less than mu, the mean. The area to the right of 980 is the total area under the curve, which is always 1, minus the cumulative proportion up to 980. So you can see from the normal curve, so the area right of 980 equals the total area 1 minus the area left of 980, which is 1 minus 0.3534, which equals 0.6466. Okay, so because every normal curve is a density curve, the area under the normal curve is always 1. The area to the left of 980 was found to be 0.3534 using software. The use of software to find areas under a normal curve will be discussed further at the end of this section. To conclude the example, about 65 of all high school seniors meet this SAT requirement of a combined math and reading score of 980 or higher. There is no area under a smooth curve and exactly over the point 980. Consequently, the area to the right of 980, the proportion of scores greater than 980, is the same as the area at or to the right of this point, the proportion of scores greater than or equal to 980. The actual data may contain a student who scored exactly 980 on the SAT, that the proportion of scores exactly equal to 980 is 0 for a normal distribution, is a consequence of the idealized smoothing of normal distributions for data. To find the numerical value 0.3534 of the cumulative proportion in example 3.5 using software, enter the mean 1,059 and standard deviation 210 and ask for the cumulative proportion for 980. Software often uses terms such as cumulative distribution or cumulative probability. We will learn in Chapter 11 why the language of probability fits. Here, for example, in Minitab's output, cumulative distribution function, normal with mean equals 1,059 and standard deviation equals 210. You can see the p is 0.3534. The P in the output stands for probability, but we can read it as proportion of the observations. The normal density curve applet is even handier because it draws pictures as well as finding areas. If you are not using software, you can find cumulative proportions for normal curves from a table. This requires an extra step. 3.7. Using the standard normal table. The extra step in finding cumulative proportions from a table is that we must first standardize to express the problem in the standard scale of z-scores. This allows us to get by with just one table, a table of standard normal cumulative proportions. Table A in the back of the book gives cumulative proportions for the standard normal distribution. The pictures at the top of the table remind us that the entries are cumulative proportions, areas under the curve to the left of a value z. Example 3.6. The standard normal table. What proportion of observations on a standard normal variable take z values less than 1.47? Solution. To find the area to the left of 1.47, locate 1.4 in the left-hand column of Table A, then locate the remaining digit 7 as 0.07 in the top row. The entry opposite 1.4 and under 0.07 is 0.9292. This is the cumulative proportion we seek. Figure 3.12 illustrates this area. Figure 3.12. The area under a standard normal curve to the left of the point z equals 1.47 is 0.9292. Table A gives area as under the standard normal curve. Table entry, area equals 0.9292. So you can see that the z-score is above the mean, and that the area shown to the left, shaded in the normal curve, has it's 92.92% of the area according to the Table A. Now that you can see how Table A works, let's redo example 3.5 using the table. We can break normal calculations using the table into 3 steps. Example 3.7. Who qualifies for college sports? Scores of high school seniors on the SAT follow the normal distribution, with mean mu equals 1059 and standard deviation sigma equals 210. What percentage of seniors score at least 980? Step 1. Draw a picture. The picture is exactly as in example 3.5. It shows that the area to the right of 980 equals 1 minus the area to the left of 980. Step 2. Standardize. Call the SAT score x. Subtract the mean and then divide by the standard deviation to transform the problem about x into a problem about a standard normal, z. Step 3. Use the table. The picture shows that we need the cumulative proportion for x equals 980. Step 2 says this is the same as the cumulative proportion for z equals negative 0.38. The Table A entry for z equals negative 0.38 says that this cumulative proportion is 0.3520. The area to the right of negative 0.38 is therefore 1 minus 0.3520 equals 0.6480. The area from the table in example 3.7, 0.6480, is slightly less accurate than the area from software in example 3.5, 0.6466, because we must round z to 2 decimal places when we use Table A. The difference is really important in practice. Here's the method in outline form. Using Table A to find normal proportions. Step 1. State the problem in terms of the observed variable x. Draw a picture that shows the proportion you want in terms of cumulative proportions. Step 2. Standardize x to restate the problem in terms of a standard normal variable z. Step 3. Use Table A to find areas to the left of z. The fact that the total area under the curve is 1 may also be necessary to find the required area. Example 3.8. Who qualifies for college sports? Recall that the NCAA uses a sliding scale for eligibility for Division I athletics. Students with the minimum GPA of 2.3 must have a combined SAT score of 980 or higher to be eligible. Students with higher GPAs can have a lower SAT score and still be eligible. For example, Students with a 2.75 GPA are only required to have a combined SAT score that is at least 810. What proportion of all students who take the SAT would meet an SAT requirement of at least 810 but not 980? Step 1. State the problem and draw a picture. Call the SAT score X. The variable X has the N bracket 1059, 210 end bracket distribution. What proportion of SAT scores fall between 810 and 980? Here is the picture. So you can see it's a normal curve, and 810 and 980 are both to the left of the mean. And so it's like the bar between them is highlighted, and that equals 980 with a z-score of negative 0.38 minus 810, which has a z-score of negative 1.19. So you take the number to the right and you subtract the number to the left of it. So you take the higher number and subtract the lower number from it to get the bar between them. Step 2, standardize. Subtract the mean and then divide by the standard deviation to turn x into a standard normal z. So if x is between 810 and 980, you convert to see that that's equivalent to a z-score of between negative 1.19 to negative 0.38. Step 3, use the table. Follow the picture. We added the z-scores to the picture label to help you. Area between negative 1.19 and negative 0.38 equals area left of negative 0.38 minus area left of negative 1.19 equals 0.3520 minus 0.1170 equals 0.2350. About 24% of high school seniors have SAT scores between 810 and 980. Sometimes we encounter a value of Z more extreme than those appearing in Table A. For example, the area to the left of Z equals negative 4 is not given directly in the table. The Z values in Table A leave only area 0.0002 in each tail unaccounted for. For practical purposes, we can act as if there is approximately 0 area outside the range of Table A. Specifically, we act as if there is approximately 0 area below Z equals negative 3.5 and approximately 0 area above Z equals 3.5. While saying the area above Z equals 3.5 is 0.0002 versus saying the area is approximately 0 makes little difference in statistical practice, conceptually it is important to remember that these areas are not actually 0. Apply your knowledge. Use the normal table. Use Table A to find the proportion of observations from a standard normal distribution that satisfies each of the following statements. In each case, sketch a standard normal curve and shade the area under the curve that is the answer to the question. Z is less than negative 0.42. According to Table A, the cumulative proportion for Z is less than negative 0.42 is 0.3372.